Hello everyone. Today we are going to continue on with our free body diagrams. Today we're going to add in when a force is pulling on an angle. So here we have a block which has a mass of 10 kilograms. So if we're to draw out the free body diagram for it right now, we have our gravitational force pulling down as always. And since it's on a surface, we also have a normal force pulling up. And if these are the only forces, then they'll be balanced. We'll be able to solve for it. But in this scenario, we have a block. It's being pulled with a force of 100 newtons, an angle of 30 degrees. So if we draw in this force, it's going to be at an angle, just like this. And compared to the x-axis, it's going to be 30 degrees above. You could call this FA because it is the applied force. Now it's very difficult to solve for this in terms of just the resultant. So we are going to want to break this applied force into components. So the way we can do this is trace the applied force up. So I'll do this in blue. So we can trace that this way. Call it FAY, and then trace the x component like this, FAX. The same way that we have in other units for different types of vectors. So now we want to analyze this scenario. So we want to take a look at what's happening in the vertical direction, just the same as the y direction. So the first thing we want to look at is going to be FAY. And just like with any vector and angle, we are going to solve for this component by doing FA sine theta, because its angle is measured in this way that the y component is the opposite of 30 degrees. So if we plug in our values, 30 degrees, 100 newtons, we will get that it is 50 newtons. From there, we can do our sum of forces equation. So in the y direction, we can do Fy equals, upwards we have the normal force, the applied force, and downwards we have the gravitational force. So we'll subtract this. It's not flying up into the air, it's not sinking into the ground, so this can be equal to 0. Then from there, we can rearrange our variables. In this case, we don't know our normal force, but we are able to get our y component and gravitational force. So in this case, we'll get the normal force by itself equal to Fg minus Fay. In this case, we can estimate our gravitational force to be roughly 100 newtons, because 10 meters per second squared times 10 kilograms, about 100 newtons. Subtract the 50 newtons, and get our normal force to be about 50 newtons up. So what we can see is that the normal force supplied by the surface is reduced by having this force act on an angle. All right, so next we want to take a look at the horizontal dimension. And here we want to find what our horizontal component is. So we can do this by FAX equals FA cosine theta. Then from there we can plug in 100 newtons with the 30 degrees, make sure we're in degree mode, and we'll get 86.6 newtons. So if this is frictionless, then in this case, we do our sum of forces, we'll find that our net force is going to be equal to FAX. So from this, we'll determine that our acceleration is only going to depend on this FAX. All right, let's take a look at another example right here. So we have a man pulls a 40 kilogram crate across a smooth frictionless floor with a 20 Newton force that is 45 degrees above the horizontal. So for to draw in all of our forces, we are going to have our gravitational force pulling down. We are going to have this applied force 45 degrees above the horizontal, and we'll also have some type of normal force. And our applied force is 20 newtons at 45 degrees above the horizontal. So we want to know the net force, and as we determined before, the net force is only going to depend on our FAX because it's not flying up into the sky, it's not sinking into the ground, so it's only going to be in the X direction. So we're going to find that the net force is equal to our applied force in the X direction, which is equal to FA cosine theta. Which, if we plug this into our calculator, 20 newtons times 45 degrees, we'll get 14.1 newtons. So now we want to know our acceleration. So using our net force equation, F net equals ma, or in this case, we'll rearrange it to be A equals F net over m. We can plug in our values. We get 14.1 newtons divided by our mass of 40 kilograms. And we will then get that our acceleration will be equal to 0.35 meters per second squared. All right, so now we have a question. What would happen to the acceleration if the box were pulled at a greater angle and then at a smaller angle? So if we continue to look at greater and greater angles, so if you're going like this and eventually upwards, then we will find that a greater angle will result in less acceleration. And in the opposite direction, if we continue down, more of it will be acting in the X direction, so we'll find that a smaller angle will result in more acceleration. All right, so now we want to take a look in which we are pushing on an angle instead of pulling at an angle. So we have a block that has a mass of 10 kilograms, which means that there will be a gravitational force pulling down. From here, the block is pushed with a force of 100 newtons and an angle of 30 degrees below the horizontal. So in this case, we will have this applied force right here, which is 30 degrees below the horizontal, and it itself is 100 newtons. So upwards, we will also have a normal force, and then we will have the X and Y components of the applied force acting as well, which we'll call FAY and FAX. And just like before, what we just did is we broke the applied force into components. So now we want to take a look at each dimension. So we'll start with the vertical dimension. So just like before, we will find the Y component, which would be FAY equals FA sine theta. By plugging in our values, 100 newtons and 30 degrees, we'll find that FAY is going to be 50 newtons. So now we can take a look at our sum of forces. We will add up all of the forces in the Y direction. So the only one in the positive direction is Fn, so that'll be our only positive number. We'll subtract FAY and FG. Now what we'll also see is it's not sinking into the ground, it's not flying up into the air, so it's equal to 0. So now we can rearrange to get the normal force by itself to find what the normal force is equal to. So we get that this normal force is going to be equal to FAY plus FG. Then from there we can plug in our values, where the force of gravity is going to be about 100 newtons, and our applied Y force will be 50 newtons. So we can find that the normal force will be 150 newtons. So since we are pushing this into the ground, we will find that the normal force supplied by the surface is going to increase. So the harder that we push this box into the ground, the harder the ground pushes back on the box, just as Newton's third law states. So now we want to take a look at what's happening in the horizontal direction. So we'll take a look at FAX, solve for what it's equal to, FA cosine theta, plug in our values again, and we'll find that the applied force in the x direction is 86.6 newtons. And just like before, if this is frictionless, then in this case we'll find that the applied x force is going to be equal to our net force. So just like before, we will find that our acceleration depends only on our x component of our applied force. Now let's take a look at one more example. So we have a girl pushing a 30-kilogram lawnmower with a force of 15 newtons at an angle of 60 degrees below the horizontal. So if we draw out our free body diagram, so we have the force of gravity pointing down, the normal force pointing up, and then we have this 15 Newton force at 60 degrees below the horizontal. So roughly something like this. 60 degrees right here. Draw out the components, FAY and FAX. So assuming there is no friction, what is the acceleration on the lawnmower? So as we said before, with no friction, then the acceleration is only going to depend on what FAX is equal to. So in this case, we have FAX is going to be equal to FA cosine theta. We'll plug in 15 newtons times cosine 60, and we will get that the applied force in the x direction will be equal to 7.5 newtons, which is also going to be our net force. So now we can solve for the acceleration. Acceleration equals F net over m. So we can plug in our 7.5 newtons over 30 kilograms, and we will find that our acceleration is equal to 0.25 meters per second squared. All right, so now we have another question right here. What could she do to maximize her acceleration? So as we mentioned before, if we continue to decrease our angle, kind of bring it more towards the horizontal, then our acceleration should increase. So in this case, in order to maximize her acceleration, she needs to push parallel to the ground. All right, and that's it for today. I hope you all have a great rest of your day.